Today, I am excited to dive into the fascinating world of Ethernet switching with you. Together, we will explore the rich history of switching development, unravel the inner workings of switching technology, and delve into the multitude of remarkable switch features. Additionally, we will embark on an enlightening journey through the intricate details of Ethernet operation. So, buckle up and get ready to embark on this captivating adventure of knowledge and discovery. In the past, LANs relied on a physical bus, using long coaxial backbone cabling to connect devices. However, as technology advanced, we witnessed a shift towards more efficient solutions. The introduction of 10 base T and UTP cabling brought about the popularity of hubs as a cost-effective and convenient means of device interconnection. Despite their advantages, hubs had certain limitations that posed challenges. Devices connected to a hub shared the same collision domain, leading to collisions when multiple frames were sent simultaneously. Moreover, broadcasts sent by one device were received and processed by all other devices on the LAN, increasing unnecessary network traffic. To address these issues, Ethernet bridges emerged as a solution. Bridges effectively segmented LANs into multiple collision domains, reducing collisions and improving network performance. They helped decrease unnecessary traffic from other segments. However, the real game changer was the advent of switches. These innovative devices not only offered the benefits of bridges, but also introduced additional advancements. Switches provided a larger number of interfaces, enabling further segmentation of collision domains into more manageable segments. Moreover, they leveraged hardware-based switching instead of relying solely on software, which enhanced efficiency and speed. When all nodes are connected directly to a switch, the network's throughput experiences a significant boost. Each computer is assigned a separate port on the switch, creating its own dedicated segment and collision domain. This remarkable transformation yields three primary advantages. 1. Dedicated bandwidth. Each port on the switch receives dedicated bandwidth, ensuring optimal performance and eliminating congestion caused by shared resources. 2. Collision-free environment. With separate collision domains, the likelihood of collisions decreases significantly. This promotes smooth and uninterrupted data transmission. 3. Full duplex operation. Switches support full duplex communication, allowing devices to transmit and receive data simultaneously. This further enhances network efficiency and throughput. So, as we explore the captivating world of Ethernet switching, let's celebrate the transformative power of switches in revolutionizing LAN connectivity, providing dedicated segments, collision-free environments, and unlocking the full potential of our networks. Switches possess the remarkable ability to selectively forward individual frames, creating a seamless, point-to-point connection between source and destination nodes. This connection is established by the switch through a clever analysis of the source and destination media access control (MAC) addresses in the Ethernet header. The primary role of a LAN switch is to receive Ethernet frames and make an informed decision on whether to forward or ignore them. To accomplish this, switches undertake three crucial actions. Step 1. Determining whether to forward or filter frames based on the destination MAC address. Step 2. Learning MAC addresses by examining the source MAC address of each received frame. Step 3. Creating a loop-free environment with other switches through the implementation of the Spanning Tree Protocol, STP. To aid in the decision-making process, switches maintain a dynamically constructed MAC address table stored in RAM. By comparing the destination MAC address of an incoming frame with the entries in the table, the switch determines how to handle the frame, whether to forward it or filter it. Let's paint a vivid scenario. Imagine a switch receiving a frame from host A, carrying a destination MAC address of OC. The switch swiftly consults its MAC table, finds an entry corresponding to the MAC address, and forwards the frame out of port 6. Notably, the switch ensures that the frame is not transmitted back through the port it was received on, effectively filtering it. Additionally, the switch refreshes the timestamp associated with the source MAC address in the MAC table, maintaining accurate information about the network. Continuing our journey, let's say a new device, host E, is connected to port 10 host B, unaware of host E's location, sends a frame destined for host E. In this case, the switch employs a technique called flooding. It forwards the frame out of all active ports except the one it arrived on, in a quest to reach its destination. The diligent host E receives the frame and promptly responds to host B. The switch, now enlightened about host E's existence, learns the MAC address and associated port, storing it securely in the MAC address table. Henceforth, any subsequent frames intended for host E are exclusively directed to port 10, eliminating unnecessary traffic. In addition to forwarding and filtering frames, LAN switches must possess the prowess to construct loop-free paths within the network. This is where the Spanning Tree Protocol, STP, comes into play. STP is a savior in Ethernet networks that harbor redundant physical links, ensuring that loops are prevented and frames can navigate smoothly to their destinations. Imagine a bustling network where collision domains abound, as multiple LAN interfaces contend for limited resources. In such shared media environments like those fostered by hubs, collisions are an inevitable consequence. However, when a host finds solace in the embrace of a switch port, a dedicated connection is forged, banishing the spectre of collisions. The switch's magic lies in its ability to reduce collisions and optimize bandwidth utilization on network segments. Each segment basks in the glory of full duplex communication, reveling in the luxury of dedicated bandwidth. Alas, not all challenges are vanquished with the switch's arrival. Broadcast traffic, like an unyielding tide, still engulfs the network. As interconnected switches form a grand tapestry, they create a vast broadcast domain. Whenever a frame carrying the mysterious destination address journeys across a switch port, a cascade of events unfolds. The switch, bereft of a direct path, must unleash the frame into the wild, flooding it out through all other active ports. Each attached device, compelled by duty, must then diligently process the broadcast frame, journeying at least up to the network layer. Switches play a crucial role in network communication by facilitating the forwarding of frames. They can vary in their forwarding methods, port speeds, memory buffering, and the OSI layers involved in the forwarding decision. Let's delve deeper into these concepts. Switch forwarding methods. Switches employ different forwarding methods to transmit data between network ports. 1. Store and forward switching. Upon receiving frames, the switch stores them in its buffers and carefully analyzes each frame for destination information. It also verifies data integrity using cyclic redundancy check, CRC, in the frame trailer. Before forwarding any part of the frame, the entire frame is stored and the CRC is calculated. If the CRC passes, the frame is sent to the destination. 2. Cut-through switching. In this method, the switch only buffers enough of the frame to read the destination MAC address. This allows the switch to determine the appropriate port for forwarding the data. Once the switch identifies a match between the destination MAC address and an entry in the MAC address table, it starts forwarding the frame, while the remaining part of the frame is still being received. Cut-through switching does not perform error checking on the frame. 3. Fragment-free mode. This method involves the switch waiting for the collision window, 64 bytes, to pass before forwarding the frame. By doing so, the switch examines the data field of each frame to ensure that no fragmentation has occurred. Fragment-free mode provides better error checking compared to cut-through switching, with minimal latency increase. Switches can operate at different OSI layers, affecting their functionality and capabilities. 1. Layer 2. LAN switch. These switches perform switching and filtering solely based on MAC addresses. They are transparent to network protocols and user applications, focusing solely on forwarding frames based on MAC addresses. 2. Layer 3 switch. Similar to Layer 2 switches, Layer 3 switches also perform switching and filtering based on MAC addresses. However, they can additionally utilize IP address information for forwarding decisions. Layer 3 switches can also carry out Layer 3 routing functions, reducing the need for dedicated routers within a LAN. Due to their specialized switching hardware, Layer 3 switches can route data as efficiently as they can switch it. Ethernet, often used interchangeably with the IEEE 802.3 standard, is a prominent LAN technology that encompasses the physical and data link layers. Here's an overview. 1. Ethernet standards. 802.3 is the IEEE standard for Ethernet. The terms Ethernet and 802.3 refer to a family of standards that collectively define the physical and data link layers of LAN technology. 2. Data link layer sublayers. Ethernet divides the functions of the data link layer into two distinct sublayers. A. Logical Link Control, LLC. Sublayer, defined in the 802.2 standard. This sublayer provides services for managing data link connections and performs error correction. B. Media Access Control, MAC sublayer. Defined in the 802.3 standard, the MAC sublayer handles media access control, addressing and frame synchronization. The logical link control, LLC sublayer, serves as an intermediary between the network layer and the media access control, MAC sublayer. Its primary function is to identify the protocol being transmitted from the data link layer to the network layer. This approach avoids populating the MAC sublayer fields with protocol-type information, as was the case in earlier Ethernet implementations. The MAC sublayer has two key responsibilities. 1. Data encapsulation. This involves assembling frames before transmission, parsing received frames, handling MAC addressing within the data link layer, and performing error detection. 2. Media access control. Ethernet operates as a shared medium, where all devices have the ability to transmit at any time. In half-duplex mode, media access is governed by a method called carrier sense, multiple access, collision detect, CCNA. This mechanism ensures that devices listen for carrier signals on the network and detect collisions in case multiple devices attempt to transmit simultaneously. At the physical layer, Ethernet specifies and implements encoding and decoding schemes that enable the transmission of frame bits across different transmission media, including unshielded twisted pair, UTP, copper cables, and optical fiber cables. In earlier Ethernet implementations, coaxial cabling was commonly used. To gain a better understanding of Ethernet, it is helpful to explore two early Ethernet specifications, 10-base-5 and 10-base-2. These specifications involved the installation of a series of coaxial cables, as depicted in this figure on the top, to connect devices in the Ethernet network. The coaxial cables formed an electrical circuit known as a bus, which was shared among all devices on the Ethernet. When a computer intended to send data to another computer on the bus, it generated an electrical signal that propagated to all devices connected to the Ethernet. The evolution of Ethernet brought about significant changes in media and network infrastructure, with the introduction of the first hubs and the adoption of unshielded twisted pair, UTP cables. Ethernet physical topologies transitioned from a bus configuration to a star configuration, as illustrated in figure on the bottom. Despite the shift in physical topology, hubs operate logically similar to traditional bus topologies and still require the use of carrier sense, multiple access, collision detect, CCNA. Ethernet shared medium nature, where devices have equal access to transmit, necessitates a mechanism to ensure orderly traffic flow. The CCNA algorithm defines how devices access the Ethernet logical bus, minimizing collisions and providing guidelines for collision resolution. The CCNA process unfolds as follows. 1. Step 1. A device with a frame to send listens until the Ethernet medium is not busy. 2. Step 2. Once the Ethernet is idle, the sender initiates frame transmission. 3. Step 3. The sender monitors the medium to detect potential collisions. 4. Step 4. In the event of a collision, each device involved in the collision sends a jamming signal to ensure all stations detect the collision occurrence. 5. Step 5. After the jamming signal, each sender randomizes a timer and waits until the timer expires before re-attempting to transmit the collided frame. 6. Step 6. When the random timer expires, the process begins anew, starting from step 1. When CCNA is in effect, a device's network interface card, NIC, operates in half-duplex mode, allowing it to either send or receive frames at a given time. However, CCNA is disabled when a NIC detects its ability to operate in full duplex mode, where simultaneous sending and receiving are possible. The prevailing Ethernet standards, namely 10-base-T, Ethernet, 100-base-TX, Fast Ethernet or FE, and 1000-base-T, Gigabit Ethernet or GE, employ unshielded twisted pair, UTP cabling. While there are some distinctions between them, such as the required number of wire pairs and the category of cabling, UTP is the common denominator. UTP cabling in Ethernet standards typically consists of either 2 or 4 pairs of wires. The cable ends are commonly fitted with RJ45 connectors, featuring 8 physical locations called pin positions or pins. The Telecommunications Industry Association, TIA, and the Electronics Industry Alliance, EIA, establish standards for UTP cabling, including color coding for wires and standardized pinouts. This figure illustrates 2 TIA-EIA pinout standards, displaying the color coding and pair numbers. For the exam, it is essential to differentiate between straight-through and crossover cables for specific network segments. In summary, if devices on opposite ends of a cable utilize the same pair of pins for transmission, a crossover cable is required. Conversely, if devices employ an opposite pair of pins for transmission, a straight-through cable is used. This table provides a list of typical devices and the pin pairs they utilize, assuming the use of 10 base T and 100 base TX standards. When it comes to 1000 base T, gigabit Ethernet, 4 wire pairs are required since gigabit Ethernet simultaneously transmits and receives data on each of the 4 wire pairs. However, gigabit Ethernet also employs the concept of straight-through and crossover cables, with a minor difference in the crossover cables. The pinouts for a straight-through cable remain the same, pin 1 to pin 1, pin 2 to pin 2, and so on. In contrast, a crossover cable adheres to the 568A standard on one end and the 568B standard on the other end. This arrangement results in the crossing of pairs at pins 1, 2, and 3, 6. Switches offer several advantages over hubs, resulting in improved network performance and efficiency. Let's explore these benefits. 1. Collision reduction. In traditional Ethernet networks that utilize hubs, all devices are part of the same collision domain, leading to potential collisions. However, LAN switches significantly reduce and sometimes eliminate collisions on the network. Unlike hubs, switches do not create a shared bus. Instead, switches interpret received frames, allowing them to be sent out through the required port rather than broadcasting to all ports. Utilize buffering techniques to send multiple frames through the same port, avoiding collisions by sending one frame at a time from the buffer. 2. Full duplex operation. Switches, when connected to devices with dedicated ports, enable full duplex operation. In full duplex mode, the network interface card, NIC, can simultaneously send and receive data, effectively doubling the bandwidth of a 100 megabits per second link to 200 megabits per second, 100 megabits per second for sending, and 100 megabits per second for receiving. This enhances overall network performance. 3. Individual bandwidth allocation. Devices connected to separate ports on a switch do not share their bandwidth with devices on other ports. Each port provides dedicated bandwidth, ensuring optimal performance. For example, a switch with 100 megabits per second ports offers 100 megabits per second of bandwidth per port. Ethernet employs specific addressing schemes defined by the IEE. The structure and assignment of LAN addresses are as follows. 1. MAC addresses. To ensure uniqueness, the IEE defines the format and assignment of MAC addresses. The first half of the MAC address identifies the manufacturer, referred to as the Organizationally Unique Identifier, OUI. Each manufacturer assigns MAC addresses using their own OUI, ensuring uniqueness. The second half of the address is assigned by the manufacturer and is never used on another card or network interface with the same OUI. This figure depicts the structure of a unicast Ethernet address. 2. Group addresses. Ethernet supports group addresses to identify multiple NICs or network interfaces. The IEEE defines 2 types of group addresses for Ethernet. Broadcast addresses. A broadcast address, all Fs, implies that all devices on the LAN should process the frame. Multicast addresses. Multicast addresses allow communication among a subset of devices on the LAN. Understanding these addressing mechanisms enables effective communication and proper handling of frames within Ethernet networks. In Ethernet communication, framing plays a crucial role in interpreting and understanding the transmitted bits. Framing refers to the definition of the fields assumed to be present in the received data, allowing the receiving device to make sense of the transmitted bits. It defines the structure and meaning of the bits transmitted and received over a network. Ethernet framing has evolved over time, with several iterations. This figure illustrates the different versions of Ethernet, with the most recent version depicted at the bottom. While we have previously discussed the commonly used UTP cabling in LANs, gaining a comprehensive understanding of network operations requires familiarity with additional fundamental concepts of the physical layer. The physical layer of the OSI model encompasses the following elements for the delivery of frames across the local media. 1. Physical media and connectors. This includes the various types of media used for network communication, such as copper cables, fiber optic cables, and wireless media, for example IEEE 802.11. 2. Representation of bits. The physical layer encodes the data received from the data link layer into a series of signals transmitted over the chosen media. 3. Encoding. Data and control information undergo specific encoding schemes to facilitate reliable transmission over the media. 4. Transmitter and receiver. Circuitry. Network devices employ dedicated circuitry to transmit and receive signals over the media. Bits are represented on different types of network media by modifying specific characteristics of a signal. The three primary forms of network media include copper cable, fiber optic cable, and wireless, IEEE 802.11. The representation of bits on the media involves altering one or more of the following characteristics of a signal. 1. Amplitude. The strength or magnitude of the signal can be modified to represent different bits. 2. Frequency. The frequency of the signal can be adjusted to indicate different bit values. 3. Phase. Changes in the phase of the signal can be utilized to represent distinct bits. The signaling method employed determines the nature of the actual signals that represent the transmitted bits on the media. Various methods utilize different attributes of a signal to represent 0 and 1 values. Although the specific signaling methods and their intricate operations are not crucial to CCNA exam preparation, understanding the concept of representing bits on the media is important. By comprehending framing and the fundamental aspects of the physical layer, you can gain a deeper understanding of Ethernet communication and network operations. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.